Hello and welcome again to another lesson in the Designing VMware Infrastructure video training series. This lesson is titled Creating a Physical Storage Design. In this lesson, we're first going to start out by reviewing the logical storage design. The logical design we created based on the design factors, those factors that drive the design based on requirements, risks, assumptions, and constraints. We're then going to look at the key storage solution decisions. What are the key decision points that we have to evaluate when we are selecting and building our physical storage design? We'll then move into choosing our physical storage solution, incorporating VMware technologies into the storage design, and finally wrap up this lesson with a discussion of analyzing for design impact. This is our recurring review of the design as we move through each phase and each portion of the design in order to ensure that we maintain a holistic view and maintain our understanding of how various design decisions affect other areas of the design. Now that you've seen what we're going to talk about, let's dive right in. Recall that we did another lesson titled Creating a Logical Storage Design that provided all the details on the logical storage design and the process and thoughts that went into creating a logical storage design. The logical storage design provides, generally speaking, 5 basic items. We have to provide in the logical storage design the summary of the total number of IOPS that the storage solution has to be able to provide. This number, along with the other numbers here, such as total capacity and throughput, are gathered by an assessment of the current environment or an assessment of the anticipated workloads that will be placed into a new environment in order to determine the total number of IOPS, the total capacity in terabytes or perhaps gigabytes, and the throughput that is required from your compute nodes to the storage solution. The logical storage design also includes a discussion of the logical storage allocation. In other words, how you're breaking up the storage into data stores to be presented to vSphere, as well as information on your recovery point objective, recovery time objective, and service level agreements. Now that you have the logical storage design created, and we have made that transition from the logical storage design to now mapping solutions into a physical storage design that satisfies the logical storage design. That's the transition from the what it needs to do in the logical storage design to how we're going to do it in the physical design. Now is the time for us to go ahead and create that physical design that corresponds to our logical design. Let's take a look at some of the key decision points that we have to consider as we look at creating our physical storage design. Among the decisions that are required as you look at mapping a storage solution into your logical storage design in order to create the physical storage design, one of the decision points is the storage protocol. Are you going to use Fibre Channel or Fibre Channel over Ethernet? Are you going to use iSCSI or are you going to use NFS? Each of these protocols has advantages and disadvantages. Each protocol has its own strengths and weaknesses. It's important for you as the architect to understand the strengths and weaknesses of each protocol and be sure to select the right protocol based on the needs of the environment. You'll also want to determine what sort of array you're going to get. 2 of the most common types of arrays are active-active and active-passive. This definition is based on VMware's definition of an active-active array being an array in which multiple controllers can simultaneously service writes for a single LUN. Active-passive means that only a single controller can service writes for any given LUN at a time. And this distinction has important ramifications with regards to multipathing configurations and overall scalability and perhaps performance. You're also going to need to consider the number and type of drives that are going to be in the storage solution. So does it use Fibre Channel or SAS drives? Does it use SATA or nearline SAS drives? Does it use solid state drives? Each of these types of drives has their own performance characteristics, the number of IOPS that they can support within a given response time, the number of terabytes or gigabytes they can store, their lifetime or mean time between failure. Each of these is unique to a particular family. You're going also to need to consider how and where you will employ any advanced storage technologies. such as data reduction or data deduplication, tiering, or caching. VMware integration is another key point. Where and how will you employ technologies such as the vSphere APIs for array integration, VAAI, for block storage, or VAAI NFS for NAS storage, or how are you going to employ something like VASA, the vSphere APIs for storage awareness, used in conjunction with profile-driven storage. And finally, among other things, you're going to want to consider the integration with or support for the backup and availability solutions that you selected for this design environment. This is something we discussed in another lesson in the course, so you'll want to be sure that whatever form of backup and availability solutions you have selected to use will work properly with the storage solution that you're choosing. Now let's take a closer look at actually selecting the physical storage solution that we're going to put into our design. As with most areas in the design factors are going to provide most of the guidance for your solution selection. I discussed with you in the lesson discussing the transition from logical design to physical design that the process of selecting a solution is a process that involves either drawing upon your own body of knowledge if you've been in the industry for a while, or doing the appropriate level of research, or both, depending on where you are in terms of your experience and exposure to storage solutions. You're going to need to gather the information that helps you understand what the advantages and disadvantages of each storage solution are. And with that information in mind, you will find that there are typically multiple ways to satisfy these design factors. In order to determine which way we should use to satisfy the design factors, then this is where we're going to have to take in a look to some other factors that are going to distinguish where one solution may be a better fit than another solution, even though they could both satisfy the design factors. Some of those other things that come into play could be the workload I/O profile. Is the workload predominantly read, predominantly write? Is it a basis of both? Does it do small I/Os? Does it do large I/Os? Does it drive lots of throughput or just a little bit of throughput? And each of these aspects of the workload I/O profile will have an impact on various other levels. So for example, the workload I/O profile will affect the storage protocol. It'll affect the RAID levels that you choose to employ if the storage solution uses RAID. It will affect the drive numbers and drive types. It will affect the type of array, and it may also affect how or where you would use any advanced storage technologies. Similarly, the application of your RPO, RTO, or SLA will also affect your storage protocol, your RAID levels, and your array type, among other things. Finally, it's important that we do not forget to consider operational aspects as well, which will affect storage protocol, advanced technologies, and VMware integration. A key example here would be that if you are an organization that has lots of experience with Fiber Channel, then choosing to use something like iSCSI or NFS would have an operational impact, because this is something that your staff and your team is not already familiar with. And this is something that we have to keep in consideration and keep in mind as we are selecting our physical storage solution. Now, I mentioned that the workload I/O profile can have an impact on a variety of different areas in the physical storage solution, and I'd like to delve into that in a little bit more detail here. Let's say that your logical design provides a maximum total number of IOPS of 10,000 through an assessment of the current workloads that are going to be migrated into the new environment, plus additional workloads that are going to be deployed, plus anticipated growth over the specified time period, and all this laid out in your design factors, all defined as requirements and risks and constraints and assumptions. You've arrived at the number of saying our storage solution needs, our logical design needs to provide 10,000 IOPS. Now, if you wanted to satisfy that using RAID 5 and 15K Fiber Channel / SAS drives, which are capable of providing, generally speaking, about 180 IOPS at a reasonable response time in milliseconds. Let me discuss or show how the read-write workload can affect the drive type configuration. If we look at a read-heavy workload, let's say 90% reads and 10% writes, we could satisfy that 10,000 IOPS with about roughly 72 of these fiber channel / SAS drives running at a 15K RPM. If we shift that workload to 50/50 read-writes, because of the RAID 5 overhead that is involved when writes are written to a RAID 5 set, that number of drives almost doubles to 140 drives to run the same number of IOPS but with a different IO profile. Now obviously if we were to change the RAID type to go from RAID 5 to RAID 1, or if we were to change the drive type, for example, instead of using FC SAS drives, we were going to move to SSDs, then that would alter these numbers. But that's the point, is that based on the workload IO profile, based on the percentage of reads versus the percentage of writes, this will have a dramatic impact on the overall configuration of the physical storage solution and the attributes of the physical storage solution. Now, this doesn't even take into consideration other things like throughput. We're talking about 10,000 IOPS, but we haven't specified what the IO size is and therefore what the throughput would be, because that would drive the type of storage protocol that we're going to use, which would affect the compute nodes and affect our network design potentially, or our storage networking design. So there's a lot of different aspects here. IOPS is just one, but it's important to understand that the workload IO profile is very important, and it's a critical piece of information that you really need to have as you prepare to select your physical storage solution to map onto the logical storage design. Advanced technologies such as data reduction, i.e. deduplication, auto-tiering, caching using flash, can also have a huge impact on the storage solution. However, this impact can be a little harder to quantify as clearly as the impact of the workload IO profile on the number of drives, simply because the effect will vary greatly from vendor to vendor and solution to solution. But if we look at our earlier example of a logical storage design that says I need 10,000 IOPS, we could potentially look at using some sort of auto-tiering solution combined with some flash storage drives or some SSDs in the array, and then based on the skew of the data, which is a measure of how much of the data is actually active versus how much of the data is inactive, we could potentially see that 5 to 7% of the data is generating 90% of those IOPS, and therefore a small amount of flash storage that could be used to store the most active data would have a huge impact on the overall drive count. Similarly, using a flash-based caching mechanism where there is an extended amount of cache supplied to the storage controllers using SSDs or PCI Express-based caching in the storage controllers could also significantly reduce the drive count, depending on whether this caching is read-only or read-write, and again, depending on the IO profile of the workload as well as its data locality. Note that data reduction technologies like deduplication or compression don't necessarily help address IOPS needs, although in some cases they may help. And also keep in mind that some advanced technologies may increase IOPS requirements. So it's important that you understand, if you choose to implement an advanced technology in the physical storage solution, what the impact of that advanced technology may be. The example that I have listed here is that some snapshot implementations from some vendors may carry an IOPS penalty as you start adding snapshots or levels of snapshots. For other vendors, there may not be an IOPS penalty. Similarly, they may say that there is a processor overhead to employ data deduplication technologies or something of that nature. Or perhaps data reduction technologies only work well with file-based solutions and not with block-based solutions. So it's, again, important that you understand all of the various aspects of the storage solution. You're going to need to draw upon your own experience or the experience of others in your organization or on your team, or you're going to need to do the necessary research to make sure that you have a clear understanding of how these different areas interact with each other and interact with other parts of the design. Now is also the time where you will incorporate any VMware specific storage technologies. These would include things like storage IO control, profile-driven storage, and by extension, VASA, and storage DRS and data store clusters. Each of these technologies is going to have an impact on your overall design. As an example, you might look at the use of storage IO control in your physical storage design. Will storage IO control have an impact? Of course. What will that impact be? Well, consider a couple examples listed here. If you're going to use storage I/O control with an array that does auto tiering, there are typically some very specific configuration recommendations from the vendor that are required to be implemented in order for optimal performance. Or consider the fact that storage I/O control requires that you use single extent data stores. So if you are considering the use of multi-extent data stores for whatever reason, and you also want to use storage I/O control, then you have a potential problem here. Similarly, if you're going to deploy profile-driven storage and VASA, or if you're going to deploy storage DRS, there are impacts that will occur on the design, and it's very important that you understand what those impacts are. With that in mind, I'd like to show you a flowchart, if you will, of a process that you can follow as you're going through this process of selecting the physical storage solution and creating the physical storage design to help understand what the impacts are and how we address those impacts moving through there. This is something that I have discussed before, so this is not new. This is just yet another way of looking at this technology to continue to get your mind thinking in that holistic fashion and constantly being aware of the interrelationships that exist between the various portions of the design. So here in this flowchart, I have a series of questions that you need to ask yourself, and you walk through this process. So we start out with the green block that says we're going to map a solution into the design. So you're going to pick a solution based on your own experience or your own knowledge or the research that you've conducted. You're going to say, I'm going to choose an EMC Isilon cluster to store my storage, and it's going to be using NFS. Okay, so then we move on. What areas are affected by the physical storage design decisions? Here we can use any of the techniques that I have discussed with you throughout this course. You could use a mind map, you could use a list, you could use a table. But this is where we go about exploring the idea of what areas are affected. From there we move on to the next question. What are the specific effects for each area? Again, here you could use a table, you could use a list, you could use a flowchart, whatever works for you, just to help you determine that if a particular area is affected, what are the specific effects for each area? Then we move on to the next question. How do these effects relate to the design factors? How do they impact the design factors? Does it cause a requirement not to be met? Does it introduce a risk? Does it heighten the danger of a risk? Does it violate one of the constraints? That naturally leads us to the next question. Are any design factors not satisfied? Does it fail to provide the necessary performance? Does it fail to satisfy the constraints? If that is the case, then we look at the last question. Does another solution need to be mapped into this design? I gave you the example earlier that we're going to choose EMC Isilon. If I walk through this process and I say, what are the specific effects? Oh, it's going to affect network. Okay, or what are the areas that are be affected? It's going to affect networking. What are the specific effects? I'm going to have to plan for additional network traffic because I'm using NFS. How does that affect my design? Well, maybe it's I have limited networking slots available in my compute hosts. Are any design factors not satisfied? Well, I'm violating a constraint perhaps on a network platform or a compute platform rather that only has 2 network interfaces. Does another solution need mapped in design? Yes, I have to find something else. So then we come full circle again, mapping a solution into the design. We say, okay, for whatever reason, based on the design factors, EMC Isilon doesn't work here. So now I'm going to look at an HP based solution using Fiber Channel. And we walk back through this whole process again. And I'm using these specific products and technologies as examples. There's nothing wrong with any of those, just to give you an idea of how you go through this process, how you ask yourself these questions and explore the answers to the questions in order to maintain the holistic view of the design, to maintain our awareness of how these areas are inextricably interrelated and interlinked. And as we change things in one area, there are going to be effects and impacts in other areas. We want to make sure we understand what those are and how to address them if necessary. At this point, I'd like to take a moment and walk through some storage designs, both logical and physical, taken from the Cloud Infrastructure Architecture case study. Now, I've referenced this document in other places in the course, and I thought it would be helpful to bring us back to this document again and revisit the concepts of the logical storage design and the physical storage design so you can see both of these concepts in action in an example design. Now, we'll start out in this document around page 6, And this is the point in the document at which the authors, or the architects in this case, lay out their design factors, their requirements and constraints. And so as you review the requirements and the constraints here are listed the requirements, and you can see that they have some pretty standard looking requirements. We've referenced a few of these as we talked about design factors and logical designs. Not too many of these are going to have a direct impact on the storage designs, but as we move forward into the constraints, you'll notice a couple of points here that will directly impact our logical and physical storage designs. Note constraint C103, which indicates that the NAS offering from NetApp has been pre-selected as a storage solution of choice. So we have a constraint here saying that our storage solution must come from NetApp. And then other constraints that indicate that deduplication is required and that volumes will use RAID 6. More accurately, this C105 constraint should be RAID DP, which is NetApp's dual disk protection solution. So looking at that, those are the constraints that shaped some of the logical design considerations. If we skip ahead now to page 8, you'll see a graphical diagram of how storage is being carved up. The logical diagram shows two different tiers of storage, a gold tier and a silver tier, and then each of these tiers will be presented out to the virtualization environment. Moving ahead to page 11, we begin to get a look of some of the details that are going to shape the design. I'll scroll up here so that you can get a look at this first section here, and note that here in this paragraph under the storage heading at the bottom of page 10, they give us the average I/O requirement for the virtual machines, and the number that has been selected here is 42 IOPS. Now recall from earlier in this lesson that I indicated the I/O profile is incredibly important because it shapes the design of the physical storage solution. So here we see part of the I/O profile information we need, and that is the base IOPS that they have measured and estimated at 42. The other part, one of the other parts, is the amount of capacity that is required. So note in this table and in this summary sentence below it, we see that they have estimated the size to be at about 50 gigs roughly for a potential virtual machine, 10 gigs of that being used in the system drive or the C drive, assuming Windows, and about 40 gigs being used on other drives. So about 50 gigs per VM and about 42 IOPS. What we don't have stated so far is we don't have the read-write percentage, and we don't have any information on the I/O sizes that will also help us understand what's going on. So as we skip ahead now to where the physical storage solution is described on page 22 of this document, we begin to see the authors and the architect of the design bring some of this stuff together. So first we take a look at here in the second paragraph, they are looking at how do we go about sizing some of this information. So we look at the backup solution that's being used. They're using an LTO4. They give you the theoretical maximum, how much can be backed up, what the RTOs are based on the design factors, one of the requirements that was listed earlier. They also indicate that the I/O requirement for a virtual machine is estimated now at 58 IOPS, and that includes the write penalty for the particular RAID technology, RAID DP, that is being used here. And then they calculate a number of virtual machines per data store and calculate that at the number of IOPS that are being required, then map that down, do some lower drives. And we'll get into a little more detail here in just a moment. As we scroll down, they lay out some physical details, the number of shelves, number of drives, number of drive types, type of controller, software being used, whether or not jumbo frames are being used. In this case, they are being used. Note in table 19 here that they do specify they're going to use a jumbo frame size of 9,000 bytes end to end, and it is important that you do that end to end. You can't miss anywhere along the way or else it won't work properly. Going down farther, they tell you some breakouts. This is specific to NetApp's particular implementation of storage, how they organize RAID groups and aggregates, and the number of drives and spares. Then they give you a diagram on the controllers and then the disk layouts. Also in here, they show that based on the RAID groups and based on the write penalties and overall IOPS requirements, how many VMs from an IOPS perspective can be supported on each type of tier. That will give them an idea of sizing for data stores and that sort of thing. And then they also indicate that they're adding some flash-based storage for caching. I alluded to this earlier on as one of the advanced storage technologies that could be used, and that would have an impact on the ability of the storage array to support that. Continuing down through here, they wrap up with some design implementation considerations. Note at the bottom of this screen here, they give you the breakdown on calculating the total number of IOPS based on the read-write percentage. They're estimating the read-write percentage at 62-38, 62% read, 38% write. So when we take our average number of IOPS, which was measured at 42, we look at the RAID penalty of 2 IOPS. When we do the calculations, then that brings us out to about 58 IOPS, incorporating the RAID penalty, and then we'll use that to determine how many disks are necessary to support the number of VMs and so on and so forth. Also in here, it talks about recommendations for the use of Ether channel or IP hash, which will impact the network design. And then also it talks about the use of jumbo frames, reducing the amount of overhead. Moving on in the rest of this section, we then start talking about some of the VMware specific technologies to which I referred earlier in this lesson. So here we have a discussion of profile-driven storage. And in this discussion of profile-driven storage, this is where the vCloud infrastructure architecture case study now maps those gold and silver tiers using VASA and profile-driven storage. Then a reference of vSphere Storage DRS or SDRS, and the use of SDRS with specific information around how it's being implemented for both the gold and silver tiers. Note that in this case, they recommend that gold be fully automated, but that silver be listed as manual only. If you get into the text, you'll see that that recommendation comes from the fact that the silver tier is also leveraging deduplication, and the interaction between storage DRS and deduplication is something that has to be monitored. And therefore, the conclusion, assessing impact of a design decision and then coming to a conclusion how we mitigate that impact, is that SDRS should be set for manual automation on the deduplicated Tier 2 silver data stores. More information on the specific implementation of storage DRS as well as its interaction with storage I/O control. And then the document goes specifically into the discussion of storage I/O control and how it's going to be used, as well as specifying whether the I/O metrics need to be enabled or disabled and if they need to be changed. And then finally, we wrap up this discussion of the storage design with a discussion of the storage APIs. In this particular case, we see another example of design impact because there was a constraint that NetApp was going to be the storage solution. We note that NetApp hasn't, at the time of this writing, provided the VASA or VAI NFS plugins that are required to leverage those particular technologies, and therefore they will not be leveraged in this particular design. This, again, is an example of how we assess design impact and an example of addressing design impact in the design. When you are bound by a constraint, that constraint will affect the rest of the design, and then you have to be able to account for the rest of that impact and go from there. That wraps up this review of an example of the logical and physical storage designs in this document, the vCloud Infrastructure Architecture Case Study, available from VMware. And that wraps up this discussion of creating our physical storage design. Let's quickly review what we covered in this lesson. We started out first by reviewing the logical storage design, reviewing the factors that were defined in the logical storage design, the broad specifications such as the total number of IOPS and total number of gigabytes or terabytes or petabytes that are required. We then moved into looking at some of the key storage solution decisions that are involved. What type of array do we need to use? What type of storage protocol do we need to use? Those kinds of things. Next, we had a discussion of how we go about choosing the physical storage solution and some things that we need to keep in mind as we select our physical storage solution. Following that, we had a discussion of incorporating various storage-specific VMware technologies like VAI or VASA, and making sure that we understand the impact of incorporating those technologies and addressing said impact where necessary. And finally, we reviewed once more analyzing for design impact, and I showed you another flowchart, another set of questions that you could ask yourself to put your mind in the frame of understanding relationships, understanding dependencies, and making sure you account for those in your design. That wraps up this lesson. Thanks for watching.